Way back at the beginning of the course, we learned about how to prove if a function is even or odd. Today we're going to look at identifying an even trigonometric function. We're going to be doing that algebraically. So this is the same definition of what makes a function even. If you recall, and a function is even when f of negative x equals f of x. In other words, if you plug in a negative number, you get the same thing back as if you plug in a positive number. For example, f of negative 3 equals f of 3, f of negative 4 equals f of 4. That's for all x values. If that's true, we say that the function is even. F of x is even. Now I want you to recall some even and odd identities that we learned for trig functions. First of all, we learned that sine of negative theta is equal to negative sine of theta. Same thing for cosecant. That makes them odd trig functions. So once again, sine and cosecant are odd. Cosine and secant are even. Cosine of negative theta equals cosine of theta. Secant of negative theta equals secant theta. Then we go back to two odd functions, tangent and cotangent. For example, tangent of negative theta equals negative tangent of theta. In other words, f of negative x equals negative f of x. So you might be thinking, well, that means then that any variation of sine and cosecant must be odd, and any variation of cosine and secant must be even. By variation, I mean transformation. However, that's not the case. Okay, you cannot just assume, for example, if I add, let's say I add 3 to cosine, I don't necessarily know that's even unless I prove it. Same thing for sine. If I subtract 2, that doesn't mean that it's still odd, and it might be even at that point. We don't know. So that's why we are going through the steps in this lesson. Also want you to remember the cofunction identities, particularly these at the bottom. They're the same identities except for it's either in terms of degrees or radians. But cofunction means, for example, sine of pi over 2 minus theta equals cosine of theta. Cosine of pi over 2 minus theta is equal to sine of theta. We're going to focus on these two at the top. An example of that would be, for example, if I were to take, let's say, 30 degrees. Okay, so sine, if theta is 30, then, I'm sorry, I should say pi over 6, right? Well, let's just, yeah, okay, so theta over 2 minus pi over 6 is pi over 3, right? So sine of pi over 3 is square root of 3 over 2, yes. But cosine of pi over 6 is also square root of 3 over 2. So if the two angles add up to 90, then the cosine of one is equal to the sine of the other. Okay, that's basically what these mean. Without further ado, let's go to example 1 after we've done the preliminary work. F of x is equal to 2 plus sine of x plus pi over 2. Is this an even function? Well, if you recall, we just saw that strictly sine function is odd. So you might think, well, this can't be even because it's a sine function. But there's some variation going on here, so maybe perhaps it is even. Remember, even is when you plug in a negative number, do you get the same result as when you plug in the positive version of the same number? For example, if I were to plug in pi over 2 into this, would I get the same answer as if I plugged in negative pi over 2? Well, let's check. Pi over 2 plus pi over 2 is pi. Sine of pi is 0. 0 plus 2 is 2. If I plug in negative pi over 2, I get negative pi over 2 plus pi over 2, which is 0. Sine of 0 is 0. Whoa, I got 2 again. Well, I can't just say that's even because I tried one x value. It has to work for all. So I need to be able to prove that. And furthermore, it might not even be the case. It might just have worked for one function. So bear with me, this proof is a little thorough and it's a little difficult, I'm not going to lie. And I remember when I first saw proofs, it blew me away and I didn't like them. But I promise you, the more you work at them, the better you'll get and the more you'll appreciate them. So here's our function, f of x equals 2 plus sine of x plus pi over 2. So what I want you to notice is it looks very, very similar to the cofunction identity. The only problem is there's a plus in between what we have. In the cofunction identities, it's minus. So we're going to try to create a minus there so that maybe we can simplify that down to just cosine. Again, step 1 is to simplify f of x. Okay, so if I can use the cofunction identity, perhaps I can just change it into cosine, right? Since I have a pi over 2 and an x. And x, by the way, is the same as theta. Maybe I can just strip it to cosine. However, this is a plus, so we need to do something about that. Well, first of all, I'm going to use some substitution. I'm going to say x plus pi over 2 is equal to theta. That way I can just strip it down to just sine of theta. It's substitution, basically. Okay, so next, what I'm going to do, I know that sine of theta is equal to cosine of pi over 2 minus theta, using those cofunction identities we just looked at. Okay, so again, the goal is to try to get a minus in here so we can turn it to straight cosine. Okay, so let's replace theta with what we said it was equal to. Okay, we said theta was equal to x plus pi over 2. So let's draw an arrow here. I'm going to replace theta with x plus pi over 2. And by the way, you don't need this substitution step. I just think it makes the proof a little bit more clear. So notice what happens now. This minus is going to distribute to both of these terms. And I'm going to get pi over 2 minus x, and it's going to distribute to that minus pi over 2. So pi over 2 minus x minus pi over 2. And look what happens. The pi over 2's cancel, and we're just left with negative x. So in fact, I was able to cancel the pi over 2's. And furthermore, what do we know that cosine of negative x is? Well, because cosine is an even function, cosine of negative x is just going to be cosine of x. And therefore, when I go back here, cosine of negative x is just going to become cosine of x. Now, this is actually really crazy to me because I didn't know this before I did this problem. But we've just proven that sine of x plus pi over 2 is equal to cosine of x. Pretty crazy. I didn't know that before. So sine of pi over 2 plus x, which is the same if you flip it, is actually the same as sine of pi over 2 minus x. They're both equal to cosine, and I just didn't know that before I did this proof, but thank God I did. So we've just proven that this is equal to cosine. And we've completed step 1 because obviously we really can't simplify that anymore, as far as I know. So I'm going to go ahead and put a check mark here. 2 plus cosine of x is simpler than what we started with. Okay, so let's move on to the next step. Now that we've got a simpler version of f of x, we're going to plug in negative x. And believe me, we've already done 90% of the work. So I'm going to plug in negative x in for x. Let's draw an arrow. I like to draw arrows. Okay, and then we're going to simplify that for step 3. Now, I know I've just shown cosine of negative x, according to our even identities, is equal to cosine of x. So for step 3, I can just say cosine of negative x is equal to cosine of x. And I forgot one thing here. One second. I forgot the f of negative x on the left side, because here's f of x, but when I plug in negative x, it should be f of negative x. And like we just said, cosine of negative x using the even identity is just cosine of x. But look what we've just proven. F of negative x is equal to 2 plus cosine of x. Well, guess what? We already know that f of x is equal to 2 plus cosine of x. That's what we proved in step 1. So what we've just done is we've shown that f of x is equal to f of negative x. They're both exactly the same thing. Again, you can see it exactly right here. Again, like I said before, 90% of the work was in step 1. This step is actually almost trivial. So for step 4, we want to write out our answer with the reason. We've shown f of x, which originally was 2 plus sine of x plus pi over 2. We proved that that's equal to 2 plus cosine of x using cofunction identities and even identities. And that's equal to f of negative x. Okay? And I know sometimes this, again, I know it can be confusing at first proofs. Just look it over, ask me questions, do you have any? All that to say that we've proven that f of x is equal to f of negative x, and therefore f of x is even. Okay, I know that was a lot, especially this page right here. Again, if you have any questions about this, let me know. I actually figured this out on my own. I made this problem up and thought about it for a while and realized, like I said, that this looks like a cofunction identity. So why not try to change it into cosine? And it's exactly what I did, and it ended up working out perfectly. By the way, before I'm done, let's go ahead and look at the graph of our original function. Okay, so here's the graph of our original function, 2 plus sine of x plus pi over 2, and you can see that it's perfectly even about the y-axis. As I show my students, if you draw a dotted line down the y-axis, you will see a mirror reflection for even functions, meaning it's the same on the left and the right. That's it for this example of proving trig functions are even. If you have any other questions about it, let me know.